Good afternoon to all of you. First of all, I thank IPI Chennai chapter for giving us this opportunity to make a presentation on the metal to plastics conversion. This topic is very valid today because we are seeing a downtrend in the automotive market, and from the plastic sector, we need to identify more applications where we can put plastics into use. My presentation will consist of three major parts. One is the metal to plastics, a brief insight into metal to plastics conversion methodology, how we have gone about it. And then I take up two case studies in which we have achieved for automotive parts along with our parent company Brakes India, and also our capability on metal to plastics conversion. A brief history. Metal to plastics conversion started quite a long time back, 1950s. The focus mainly from automotive and aerospace companies. Aerospace companies use as much as about 25 to 30% of metal to plastic components. And they were the most active in converting metal products to plastics. The main drivers were to reduce weight and to improve fuel efficiency. With proper design, material selection, engineered plastics can be made to work as strong as metal. One fundamental thing that we need to understand before we take up this metal to plastics is that plastics are basically different from metal in terms of the molecular structure. You can't have a one-to-one, you can't have an apple-to-apple comparison between both metal and the plastic. They're basically two different materials. I think this is something that we need to fundamentally understand before we go into any conversion. And metals differ from plastics, or the plastics differ from metals, not only in the short-term properties, but also in the way they react under applications to influences of time, temperature, and load. It's not that they are inert for a long period of time and for long temperature cycles and for long loading cycles. The typical benefits, what you would have from such replacements. One, the most foremost is what people look for is the weight reduction. Because basically all plastics have lower densities compared to metals. Most of the plastics are well below 2, while metals with aluminum starting from 2.7 and going up to the steels about 8. Fewer assembly operations can be achieved. Secondary finishing processes can be reduced substantially. Total system cost can be reduced. Basically, plastics are electrically non-conductive. We have today plastics which can resist up to 250 degrees centigrade, which is a normal working temperature, which is well below the normal working temperature in an automotive application. And resistance to most chemicals and corrosive environments. We have greater design freedom with plastics. The part complexity can be designed depending on the requirements opportunities for parts consolidation. You may have multiple parts, child parts in a metal assembly. Well, that can be consolidated. We can reduce the number of child parts in a plastic assembly. With the wide variety of materials available, plastic materials available today in the market, you can have a very broad range of properties and which can be tailor-made to suit specific requirements. Basically, energy efficient plastic processing is considered to be much more energy efficient compared to metal part production, such as die casting or sand casting. And in terms of maintenance, they relatively have very low maintenance costs. They do not require any coating, painting, etc. And today plastics are also, the colored plastics, engineered colored plastics are playing a very vital role in the automotive interiors where they are replacing many metal parts which are painted. There's just a comparison of the density values where you have the metals ranging from 2.5 to 8. And most of the engineering plastics have between about 1.4 to about 1.8 or maybe 1.9. One is the design freedom with plastics. With the wide material selection, you have a wide range of plastics. You can have more complex geometries. And the processing method, injection molding conventionally, can allow you for undercuts, threads, ports, and tight tolerances. So basically, in a single shot, you can try to get the final product without doing any secondary operations. Flow characteristics can be monitored and they can be modified in such a way that can have very low wall thickness products. And when you consolidate and when you make a plastic part replace, you can have inbuilt structural strength for the plastic part by provision of ribs, bosses, gussets, instead of having a very solid thick part. And this can avoid many other normal processes such as fastening or welding or gluing, which is normally seen with the metal part. And this can increase the total strength of the full assembly. The current trends in conversion mostly focus on reducing weight. It's one of the major, improving the strength, better corrosion resistance, consolidating multiple parts into one single plastic parts, and mainly achieve same tight tolerances with fewer secondary operations. And the overall estimate is about 25 to 50% reduction, because otherwise the conversion really doesn't work. Customers are not happy, OEMs would not be happy. They would require a fairly good cost savings. And this will be about 25 to 50% cost reduction in the plastic part. When you do a switch, when you do a conversion from metal to a plastic, what factors would you look into? First of all, you have to evaluate whether it's really viable, whether it's really suitable for going into such a conversion. So what do you achieve by doing this? It's very difficult to blindly go into any metal to plastic conversion and then finally come back and say, no, it's not workable. So you should look at things like whether you want a better part, which is less costly to manufacture, with some more superior characteristics, added advantages over the conventional metal. What are the change drivers, weight, strength, aesthetics, or environmental issues? These are some of the driving factors for the change which need to be considered. We also need to look at the end-use applications, environmental conditions, and last but not the least, the cost benefit, the economic feasibility of conversion. Do a cost benefit analysis for understanding whether it's really beneficial to change over to a plastic. One is the material, what you use, and then the production process. If you do an injection molding, you do require a mold. It could be a simple mold, it could be a complex mold, depending on the part geometry. And also you need the machinery. This is also expensive. Will it add to the overall cost of the plastic part? Plastic material prices sometimes can go haywire, so we need to factor that also. How much scrap will you save if you do a metal to plastic conversion? Is it by a cold feed system or at a hot runner system? Can you save on the feed system cost also, depending on the plastic you choose? The volumes, very small volumes really do not give you a good value addition. What sort of volumes are you looking at? Another factor which really people look at today is how the process can be automated. Plastic molding is a very fast process with cycle times of less than a minute. So how can you automate the entire system so that you have better cost advantage? And in terms of overall quality, cost to manufacture, product life, and functionality, what is the total gain that you get from converting from a metal to a plastic? In terms of material selection, which is one of the key important aspects of this conversion process. Today you have a wide variety of compounded, you have plain polymers, you have polymers from the reactor, polymers which can be compounded with specific fillers, reinforcements, additives. All this can give you a great amount of structural integrity into the plastic part. So choosing the right plastic also takes it takes some amount of time, a lot of study, a lot of deep insight into understanding the properties of the plastic, understanding their long-term behavior, and you have to choose the right plastic to make it happen. And today, from the plastic library, you have more than 25 to 30,000 engineered polymers, which consist of the unfilled, filled, and modified polymers. So you have a wide range of materials based on their temperature, continuous use temperature, load-bearing characteristics, etc. to choose from. And you have also a lot of polymer alloys. Polymer alloys are gaining a lot of ground today in replacement, metal replacement. And these polymer alloys can be tailor-made to suit the requirements of the part. Key considerations would include whether you require a crystalline or amorphous polymer, depending on the type of application, chemical resistance, impact, flow, ease of processing. What type of additives would you require to make the plastic work as a suitable replacement? It should have high strength, stiffness, temperature performance, appearance, and also easy for packaging, and last but not the least, cost. The plastic should also be able to take up, should be easy to where you can incorporate fillers like carbon, stainless steel fillers specifically for conductive or shielding EMI applications. For friction and wear properties, you will have specific lubricants. You can use specific lubricants which can improve the wear characteristics. Most of you would know that mineral fillers are normally added to reduce cost. But they can also improve electrical performance, lightweight, sound dampening, and improve dimensional warpage reduction, etc. Rubbers or elastomers would improve the toughness of the material. The design of the plastic is a chapter by itself. At the time provided would not be able to discuss too much on that, but I'll just touch upon this. The design engineer, the design engineer plays a very pivotal role in designing the plastic part. So he must be able to accurately predict what would be the real environment in which the plastic part would be subjected to. So chemical exposure, temperature resistance, and also he should have a fairly good idea on understanding what would be the worst case scenarios, under what extreme conditions would the plastic part be subjected. And today we have many softwares, FEM tools which can clearly help us to understand what would be the ability of the plastic to meet the requirement without even any major investment in tooling or in even material. FEA would give stress analysis, deflection, optimization, part design optimization. And material flow analysis would give details on the flow balancing in the mold, pressure distribution, weld lines, fiber orientation, etc. Ultimately, it requires a very close collaborative approach between a part engineer, a materials engineer, mold designer, and the molder to make a successful metal to plastic conversion. A silo approach would be a total failure in this case. I can very clearly tell you this. It would require a very, very close collaborative approach to achieve this, and a very integrated. The inputs, summarizing this would be the inputs would be the technical data on the part, the machine software, team of skilled and experienced engineers, tools for comparing cost and energy effectiveness. The process would involve concept stage to production stage, choosing the plastic raw material, plastic design modification, analysis, simulation, prototype development, mold development, trials, testing and correction, and finally part optimization and production. With these inputs and the process involved, the output would be a successful replacement of a metal with plastic. I will now take you through two case studies quickly, which we have done along with our Breaks India Advanced Product Development Engineering team on two very successful metal to plastic replacements. One is a clutch master cylinder. This is a metal to plastic conversion. It's a clutch master cylinder housing. The part has been conventionally made in cast iron and maybe also in aluminum. And this has been converted to a plastic. Most of you would be aware of the clutch master cylinder working principle. So basically, when you press the clutch pedal, the push rod contracts the plunger and pushes it inside the bore of the cylinder. After about 1 mm movement, the valve seal closes the inlet port to the supply tank. As the plunger continues to move inside the bore, fluid is forced through the Bundy pipeline to the slave cylinder. And when the clutch pedal is released, the plunger moves back with the return of the fluid from the slave cylinder. We are only talking about the master cylinder. There's another slave cylinder also. This is the rough construction of a master cylinder, clutch master cylinder. We had this particular part which we had taken was being supplied to M&M and to TML. The bore size was 19.05 mm dia. The stroke length was 35 mm. And the weight was almost about 1 kg. The target was to reduce it at least by 50% initially. The steps in this product development: first, benchmarking. Fortunately, in this case, we had some products which were in the market. Then design proposal, feasibility review, part development, validation, and launch. We identified certain products which were of similar, maybe design or maybe the function, made by other suppliers. The second stage was the design proposal. The part requirements were identified clearly at this stage. It should be suitable for very high temperature. Continuous use temperature was fixed at about 140 degrees centigrade. It should have very good brake fluid compatibility, very good dimensional stability, and a very good surface finish, especially inside the bore. And this surface finish should be attained as molded, not by any secondary operation. It should be as molded. This was a very major challenge. And we should also have built-in inserts. This cannot be inserts cannot be added as a secondary process. The insert should be as molded. So it was sort of an insert molding. After a lot of FEA study, then we finally arrived at the material. The material was polyacrylamide, which was with, here it's 50% glass filled material. We looked at how many parts could be consolidated in the whole assembly and what could be removed, what could be built in along with the plastic part when we do the injection molding. There are also certain other metal parts in this. So it has to, the plastic housing had to accommodate all these parts. The construction of the mold. And here we learned about the use of laser fusing, conformal cooling. The bore had to be with very accurate temperature control. Otherwise, it was very difficult to achieve the surface finish. The surface finish is very critical for the plunger assembly movement. It had to have a surface roughness of about 0.2 Ra. Then we started with the part development. First, we went through the mold flow analysis. We were able to do the dimensional study. We identified which is the best gate design for this part. How would the filling pattern vary if any other alternate gate designs were provided? The shrinkage, material shrinkage and the part shrinkage. Process parameters, what would be the best process parameters that would be required to mold this part? Once the part is molded, then how do we inspect this part? So we had to use special gauges for this, not the conventional ones, the special electronic plug gauge. Then a boroscope had to be used to check whether there were any problems or defects in the bore. Any scratch mark in the bore or any other defect in the bore could very seriously affect the movement of the plunger and can lead to a failure of the part. We also had to do tomography to understand whether there were any internal cracks inside the part, any porosity inside the part, because this can also have a very catastrophic effect on the part when it is when it goes into the field. And finally, an integrity test to find out what would be the actual burst strength of this part, under what conditions it would withstand, what levels it would be able to withstand. So with all this tests, then we had the product validation, in-house tests were conducted, durability run with the support of the OEM, field trials, customer DVP. In terms of in-house part, it had to undergo an ambient endurance of 1 million cycles, heat endurance at 70 degrees for 250,000 cycles, heat endurance at 120 degrees centigrade, 70,000 cycles, cold endurance test at minus 40 degrees centigrade, burst strength test, minimum 100 bar, vibration, ambient endurance, and life durability tests. In August 2012, in the initial validation stages, we ran it for 75,000 kilometers, out of 50% was in highway, then 25% in city conditions, 50% in rough road, and 10% in kart conditions. And this was the run route map. What were the parameters which were measured after the 75,000 kilometers test? Efficiency at 35%, at 35 bar, then peak pressure in bar, and the pedal effort. Overall, it went through all these tests successfully, and we were finally able to launch the product in January 2015, and it was accepted by the OEM Tata Motors also for Tata Sumo vehicles, Tata Sumo Grand vehicles. Another quick one is a plastic clutch booster. This is again an aluminum part. This was converted into a plastic. This is a part of an assembly which is a clutch actuating device for disengaging and engaging the clutch of the commercial. This is in a commercial vehicle. This booster is a part of an air and hydraulic unit that provides power assistance whenever the driver presses the clutch pedal. So basically it is utilized to reduce the effort of the driver. So again, the product comparisons were made with aluminum and with identifying the high engineering, what the performance polymers, the density, strength, temperature resistance, wear resistance, brake fluid compatibility, surface finish, cycle time, etc. In terms of blank weight, the aluminum was 450 grams, finished product weight was 270 grams, while the high performance polymer nylons were chosen for this. The finished product weight was 113 grams. There's a substantial cost reduction, substantial material weight reduction in this. Again, required for high temperature, fluid compatibility, dimension stability, and surface finish. A similar process was also done here. And finally, the product was launched from January 2018. This is mainly for commercial vehicles. So what these two projects helped us to understand, apart from this, there were many more projects on which we were able to horizontal deploy. And Sundaram Polymers, part of Brakes India, today is able to offer its technology and services mainly for developing art-to-part solutions under a single umbrella. So our aim is to provide the customer a complete solution for any drawing or any design that he gives, which is the input from him, for a metal to plastic conversion solution. Thank you all very much.